take everything we've done for curve sketching and summarizing and put it together and then try to sketch some longer type questions. Okay? Some of the curve sketching summary stuff is stuff you've known from previous years. You know how to find x-intercepts and y-intercepts. Very important to label those on your graph if you can find them. Sometimes you won't be able to find an x-intercept without technology, but often you can factor to find that. Vertical and horizontal asymptotes. This is something that you can take from last year in grade 12. You know that you're going to have vertical asymptotes at non-permissible values. Sometimes there's holes, right, if that non-permissible value canceled out, but that's something you can take from previous years and label all of your asymptotes. Then step 3, step 4, and step 5, this is where we get to use, yay, our calculus, right? And you'll get good results, even though I still have to make a frown here for concave down. So we can do our first derivative, find out where things are increasing and decreasing, and find out our maximums and our minimums. We can do our second derivative and find out where things are concave up and concave down. We can find, okay, again, you have to take this word out, because it's not the second derivative test there. Whew. Second derivative test finds maximums and minimums. So here's our first example. Starting off with your intercepts. Can you do the mental math to find your x-intercepts and y-intercepts? I'll show you the result in a couple of seconds. But try it first on your own. So I've sort of got things sectioned into different categories according to the curve sketching summary that we had before. Once you've got your x and y intercepts, you can double check by looking up. Three x-intercepts, one y-intercept. 0, 2, and -2 for your x-intercepts. Y equals 0 for your y-intercepts. Now, at this moment, I would start graphing. I'm not going to click this because you'd see the whole graph. But I would start by labeling those points. I know where my x-intercepts and y-intercepts are. I'll label those points. Does this graph have any asymptotes? No. Step 2 is easy. No asymptotes. No non-permissible values. It's a polynomial. You know its shape already. No horizontal asymptote. Find our first derivative. Let's set it equal to 0. We get plus or minus 2 over root 3. Can also find our second derivative. From our first derivative, we can label the points where it was equal to 0 and do our sign diagram to figure out our original function needed to be increasing, then decreasing, then increasing. And we can write the intervals if we want to in interval notation. If it was asking you to graph, you wouldn't need to write those intervals down. But some questions it does ask you which intervals is it increasing, which intervals is it decreasing. Draw the same thing, number line for our second derivative. Concave down, concave up. Draw your sad face and your happy face. And again, you could write the intervals where it was concave down and where it was concave up. Now, if we want to add this information to our graph, we need these points. What the first derivative finds is just the x-coordinates of possible maxes, mins, stationary points. What the second derivative finds is just the x-coordinate of possible inflection points. So if we want to find the actual coordinates, we have to plug in those values into our calculator. And what I've done here with the values is I've also shown the second derivative test to remind you. Okay? Step 4 here would be using the first derivative test to say at negative 2 over root 3, we have a maximum. Because it's increasing before, decreasing after, and our first derivative is equal to 0. What I have here is the second derivative test. Since the first derivative is equal to 0, and since the second derivative is concave up at 1.15, that makes that one a local minimum. And at negative 1.5, it's concave down. That makes it a local maximum. And our inflection point, well, we already knew at 0 we had the point 0, 0, so you wouldn't have to plug that in again. Hopefully not. And we take these 3 points along with our x-intercepts and y-intercepts. And now you can draw the graph with the sections that are increasing, the sections that are decreasing, and the inflection point. So for me personally, I like to start from my inflection point and then go through my other points. This part is concave down. This part is concave up. Some people just like to graph it from left to right and go through all their points. Either way is fine. I want you to do all the steps, find your intercepts, check for asymptotes, find your derivatives, do both number lines, find all your max-min inflection points. I would like you to do the second one on your own. I'll put the answer up in a second. For your intercepts, did you find 0 and plus or minus the square root of 5 over 3, which is approximately 1.29? When x is 0, your y-intercept is 0. There are no asymptotes. Find your first derivative. You have 3 points, 0, 1, and negative 1. Find your second derivative. You have 2 places, 0 and plus or minus the square root of 2. Is that okay where I've scrolled down? Okay. So now you can, oops, that's not what I wanted to show. Here. I didn't want to show that. Next, you can do your number lines for both f prime and f double prime. I'm trying to click in the method, like the exact order I would do it in. I usually find all my points at the end. Once you found those things, if you wanted to find those points right away, you could do that as well. From my first derivative test, I know that -1 is going to be a local max. 1 is my local min, and 0 is going to be a stationary point of inflection. From my second derivative, I know that it's concave down, concave up here, and concave down here. And of course, you could write the intervals if you wanted. In this situation, I don't think it's necessary to write the intervals. Are you okay if I scroll up for a bit? You got your sign diagrams? In this next section, the next thing I would do is find all of my points. I plug in 0, 0, I know that's a stationary point of inflection. I plug in 1, 1, -2 is a minimum. And in this box, I also put the second derivative test. The reason the second derivative test is forgotten the most easily, is that the easiestly? The reason you forget second derivative test is because after you do your number line with the first derivative, the second derivative test is not needed. So it's easy to forget it. That's why here I'm just putting it in again. I also know that it is a minimum because the second derivative at 1 is greater than 0. I know that this is a stationary point of inflection because the second derivative at 0 is 0 as well. And it changes concavity. Point 3 I know is a maximum, and I can use my second derivative test as well. Point 4 is my first inflection point, and point 5 my second inflection point. Notice with point 4 and point 5, technically we've got decimal answers there, which is a calculator. Now, if you are allowed your graphing calculator on a curve sketching question, you can figure out a lot of stuff pretty quick just by looking at the graph. Okay? But finding that stationary or non-stationary point of inflection, that could be a little bit tricky with your graph. Yes?
Your graphing calculator find a point of inflection?
What you could do on your graphing calculator to find a point of inflection, okay? It doesn't, like from this graph, if you just graph this, there's no way to quickly find these 2 points, okay? But we saw in the video the other day how to graph the derivative. Remember that? And if you graph the derivative, your inflection points are going to be maxes and minimums of your derivative graph. So I could, right, go to my calculator here, go to y equals, and I'm going to just type in 3x to the 5 minus 5x cubed. Clear this out. 3x to the 5 minus 5x cubed And in y2, I'm going to go to my math button. I'm going to go down to the derivative and do d dx of, and here you can go alpha f4 to your y variables, and I can just type in y1. I could have skipped typing in y1 and actually typed in 3x to the 5 minus 5x cubed. And this finds your derivative at any value you want, but if we go x equals x, can you see that the minimum of this W graph, the red one, is right at our inflection point? So I could, if I wanted my calculator, I want to show you some other, since we're doing calculator stuff, your graphing calculator has a lot of cool options, but sometimes we don't know how to find them easy. So I'm going to show you a couple things. I'm going to go second, calculate. I'm going to calculate a minimum, 3, okay? And notice that if I use my up and down keys, it switches which graph I'm on. I'm on the blue graph? No, I want to find the minimum of my red graph. So I'm going to go to the left side, enter, of my red graph. I'm going to go right side, enter, and a guess. And I've got my minimum at negative 0.707. And some of you might recognize that 0.707 is root 2 over 2 or 1 over root 2. If you know that, then you know you've done too much math for too long. If you don't recognize that, perfectly fine. That's cos of 45 degrees right there. Well, no, it's negative, so it'd be cos of 135 degrees. Okay, so this is my x value, which we knew was 1 over root 2. But sometimes you have an x value like this that you want to use for something else. If I quit out of my graph and I hit my store button and go to x, it remembers the last thing that you calculated, which even though it was on your graph, it stores that x value from your graph. Because sometimes you want to use that value for something else. In this case, I wanted to use this x value to figure out what it was on my blue graph. So now I'm going to go second, calculate again a value, and I want the value to be what I just stored it as, 7.07. Now it's on my blue graph. Toggle down, it's back on my red graph. Toggle up, it's back on my blue graph. Ooh. I'm terribly curious if I could have used the toggle keys last time. So there's my 1.2324 that we figured out before. I'm going to just go second, calculate. I'm going to find the other minimum, number 3, on my red graph. I want to find this one, so I can push enter for left, enter for right, enter again. It finds that value. If I toggle up, does it go to my blue graph? It does! Okay, sorry. That's new for me. I got a little excited there. That's pretty cool. So we can steal values from one to the other that way, and sure enough, those were our 2 inflection points. So does our calculator find our inflection points? Possibly, but not, there's not like a maximum min. There's not like an automatic inflection point thing. Does Desmos have inflection points automatically labeled? I don't think so. You start scrolling over, it'll be like, hey, here's a maximum, here's a minimum, here's an intercept. It likes those ones, but it doesn't have that inflection point. So some tricks to do with the calculator for those things.